Hi everyone, my name is Jan and today I'm going to show you how to build a neural network from scratch in Python. Let's start by understanding the concept of a neuron. We imagine a neuron as a simple object that first of all doesn't exist in a vacuum but interacts with a number of inputs. These inputs can come from other neurons or from an input vector, depending on the position of our neuron inside the network. The important thing is that these inputs are scalar values that flow into our neuron. But before they get there, every input value is being multiplied with a separate weight. All the inputs multiplied by their weights get summed up inside our neuron and a bias is added. We imagine all weights and the bias as parameters that influence the output of our neuron and that can be changed. And in fact, changing these parameters is what makes a neural network learn, but more on that later. The output that is produced by a neuron gets transformed by an activation function that makes sure that very large values don't disturb the network, and then the output will be distributed to other neurons or used as the output of the network, and that's a neuron. Let's have a look at neural networks. Basically, they are collections of neurons that are somehow connected to one another. They are organized in so-called layers. Every neuron inside a layer is connected to every neuron in the next or previous layer or both, but none of the neurons inside one layer are connected to one another. There are three different types of layers: the input layer, that takes in an input vector, a number of hidden layers that we can freely choose that approximates the function the neural network should learn, and finally the output layer, that produces the result of the network. Neural networks always get the task to approximate some kind of function that should be learned. To illustrate that, I chose f of x equals 2x that our network should learn. In the beginning, all weights and biases are initialized randomly. Our network gets an input, for example x equals to 1. The neurons add their weights and biases, and the output is pretty terrible at first, because the weights and biases are set randomly. However, we do know the actual result of f of x equals 1, which should be 2. What we can do now is calculate the difference between our output and the actual result, which is called applying a loss function. When we have computed our loss, we feed it backwards into our neural network and calculate how much every single weight and bias needs to be changed in order to approximate the result. And we do that by deriving our loss with respect to the different parameters. This is called backpropagation, and it makes the neural network learn, so that the output for the next values gradually get better and better. We will start building our neural network by defining a parameter, followed by a neuron, followed by a layer of neurons, followed by a neural network. And last but not least, we have to apply forward pass and backpropagation. Let's get started with programming. I've imported the basic packages math, numpy, matplotlib and random to help us build our neural network. The first thing we do will be defining our parameters, which we will later use to describe all inputs, outputs, losses, weights and biases of our neurons. We start by writing the init function. The goal is to set this class up in a way that later allows us to do backpropagation as easily as possible. Therefore, a parameter should contain a value, a list of children which should be empty at initialization, and an operation. We say self.value equals to value, and we initialize a gradient which will store the information how much this parameter needs to be changed to reduce our loss. Afterwards, we set self.children to children and self.operation to operation, as well as self.backprop to an empty function that we will define later. We will need the children later to connect the parameters the way we need them, and we need the operation because we will need to compute derivatives, and they depend on the type of operation. Now we can set a sample parameter a and print its value and gradient, but until this point this is nothing too special. Next, we need to define operations, because Python doesn't know how to perform calculations with our data structure. Let's start with the add function. Its input should be self and other. We need other to be a parameter as well, which is why we need to check and potentially transform it. Then we set our result by creating a parameter that adds up self.value and other.value, gets self and other as children, and gets a plus as operation. And finally, we will return the result. Now let's create two parameters and add them up to see if this works. Don't forget to print the value of the parameter and not the parameter itself. Now we saw that addition has worked out fine, but multiplication doesn't work yet, so let's continue with the multiplication function. This will basically look exactly the same as the add function, with the only difference that we multiplied the value of self and other instead of adding it. Of course, we need to return the result, and then we should see that multiplication also works. By the way, I added a so-called radd function that calls the add function if self is not a parameter, so that we don't encounter this issue. We see that subtraction also doesn't work yet, so let's continue with defining this function. Here we can make our lives easier because we have already defined addition and multiplication, and we can just say self minus other equals to self plus other times minus 1. Now we need to add the activation function for our neuron. We will use the value function for that just returns x if x is bigger than 0 and otherwise returns 0. Let me quickly visualize it for you so that it's easier to understand. Here you can see it. It's actually the easiest activation function. Now let's get this into our parameter class. I'm firstly gonna copy paste this, then I'm replacing the input parameter with self instead of x and create a parameter of the result. And of course, we need to work with self.value in order to get the value of our parameter object. course, our result parameter will also need to contain a child, which will be self in this case, and an operation, which will be value. Let's take a minute to understand the concept of backpropagation. Our goal here is basically to find out how much we need to change every parameter in order to make our loss smaller. Let's imagine a new one backwards for this. We have a set of parameters that we want to perform backpropagation on, beginning with our loss object. The start of backpropagation is fairly simple, because we just have to ask ourselves how much we have to change the value of the loss object in order to change the value of the loss object by 1. Of course, this is 1, and the question is kind of ridiculous, but this is the way how we will keep on going with backpropagation. Every parameter we ask ourselves by what extent the value of our loss would change if we change the value of the parameter by 1. And the chain rule allows us to multiply our results for every parameter with the result of the next parameter in order to progress through the network. So the next question is how much the loss changes if we change the input of our activation function by 1, which is just our previous derivative times the derivative of our activation function. And we continue this process all along the network for every parameter. Now let's get back to programming. We need to define our derivative functions in the next step, which we have called backward in the init function of our parameter class. Let's start with the derivative for an addition. In order to understand the derivative for an addition, let's imagine a simple function f of x equals to x plus 1. Let's see how much the output changes if we increase x by 1. Of course it increases by 1, which means that the derivative of an addition function is 1. So let's write the backward function. We store the derivative value inside the gradient parameter, and we set self.gradient and other.gradient to the gradient of the result. This is because we have to chain the derivatives of self and other with the derivative of the result, and we know that the derivatives of self and other are 1. Now we just need to set result.backprop to backprop, and we're done with this. Let's continue with the derivative of multiplication. Let's imagine f of x equals 2x for that. How much does f of x change if we change x? The answer is it changes x times the other value, which is 2 in this case. So let's write the backprop function for that. The derivative of self is other.value times result.gradient, because we need to chain it with the result again. And the derivative for other will be self.value times result.gradient. Don't forget to set result.backprop to backprop again. The last derivative we need will be the one for the value function. This will be very similar to multiplication, but we need to make sure that result.value is only taken into consideration if it's bigger than 0. Then we just chain it again with result.gradient and we're done. Now that we have all local derivatives, we can write the backpropagation function itself. We will start by setting up a list of all parameters we want to backpropagate through in the correct order. We will use the children property of the parameter class for that. Because the same parameter can be a child of multiple other parameters, we need another list that stores the already visited parameters. So we build a function that firstly checks if a given parameter has already been visited, and if not, appends the children of the parameter to the params list. Once we have that, we set the gradient of the root parameter to 1, as we've already seen in the backpropagation part. Then we loop through all parameters in reversed order as we're doing backpropagation, and just call the backward function for every element. And that's it. And now we're finally finished with the parameter class. Now we can finally create the class for a neuron. By the way, don't worry, the hardest part is already behind us. We start with the init function. A neuron will get a number of inputs as its input parameter. Then we're gonna randomly initialize our list of weights, one weight for every input parameter, and a bias that will be 0 at first. And that's already it. Next, we're gonna need a call function that will sum up all the inputs multiplied by the weights and add a bias. And that's all a neuron does, as you remember from the beginning of this video. We just need to add our activation function and then return the result. Finally, we need a function that returns a list of all parameters that belong to the neuron in order to perform backpropagation later. And that is already our neuron class. Let's continue by defining what a layer should look like. As you remember, a layer is a set of neurons that is completely connected to the neurons of the next layer or previous layer or both. Let's begin with the init function again. A layer needs a number of inputs and a number of outputs. Then we're gonna initialize a set of neurons which should each get the number of inputs defined for our layer. And the number of neurons should be equal to the length of the number of outputs defined for our layer. Next, we need a call function again, which will get a parameter x that represents the inputs for our layer. We're just gonna call every neuron in the layer for the set of inputs and return the list of outputs or just the first value if the layer only consists of one neuron. This might be the case for the output layer. Finally, we need a function again that will return all parameters for all neurons in our layer. Therefore, we're just going to call the parameters functions of all of our neurons. And that's our layer. Last but not least, we will create our neural network. So let's start again with our last init function. A neural network will get a number of raw inputs and a two-dimensional list of outputs that represents our layers with their respective numbers of neurons. Next, we're going to create a so-called size array that combines the raw input of the network with our layer sizes in order to create the layers of the network, because the first layer will need to get the raw input also. So now we're gonna look through our sizes list and create the layers. Then we're gonna create a list that stores our training progress so that we can later evaluate how well the network is trained. We continue again with the call function, which will get a list of inputs x that we want to create an output for. What we're going to do now is loop through our layers and just execute their call functions, which will trigger the call functions for the individual neurons automatically. After we're done with this, we can just return x, which will be the output for our neural net. Now we will need our parameters function again in order to return all parameters of the whole neural net for backpropagation. Therefore, we're just going to call the parameters functions for every layer in the network, which will again automatically call the parameters functions for every neuron, and then we're going to have all parameters. Now last but not least, let's create our training function. It will get a number of input vectors, x's, the desired outputs, y's, the number of training iterations, and the learning rate that will determine how much we're going to change the parameters of the network after every training iteration. We will start by simply creating a training progress list that will store the losses after every training iteration. Now we're going to initiate the training process for the number of iterations by creating a loop. Inside that loop, we're firstly going to make a prediction with our neural network for every input vector in x's. Then we will determine the loss using the mean squared error method. We will calculate the difference between the output and the desired result for every vector in x's and y's and sum that up in one parameter. Then we can append the loss to our training progress list. Next, we will call the parameters function to get all parameters of our network and set their gradients to 0 to only consider the derivatives for this respective training iteration. After that, we're just going to call the backpropagation function on our loss parameter, and it will automatically perform backpropagation on all parameters on the network, because the children of loss are the parameters of the neurons inside our output layer, and every neuron inside our network is connected to all neurons of the previous and next layer. The last thing I'm doing here is to loop through all the parameters of the network again and change the weights and biases by the value of the gradient times our learning rate times -1. The -1 comes from the fact that the gradient tells us how much the parameters need to be changed in order to maximize the value of the root parameter, which is our loss in this case. And of course, we want to minimize it, so we have to do the opposite. Now, after we set self.training progress to training progress, we're completely done with our architecture. Let's watch our network in action. We wanted to approximate the function from the beginning, f of x equals 2x. So the first thing we do is to create a dataset x's which contains some inputs, and then we're going to add the desired outputs to the dataset y's. Next, we initiate our neural network with one war input. We're going to train it with x's and y's for 100 iterations and set the learning rate to 0.01. And now we can plot the training progress and see that it really learned after we reinitiated one time. And we can see that the outputs for different input values approximate f of x equals 2x, although it's not perfect yet. But we have successfully built a neural network right now. I hope you liked it, and I'll see you in the next video.